How can the universe, with its billions of galaxies, be almost entirely made up of something we can't even see or touch? What hidden forces keep everything together? Or, on the contrary, cause it to expand uncontrollably? How small is the smallest thing that exists? Most of us take day and night for granted, the sun shining, the moon orbiting around us, but we rarely stop to think about the astonishing story of everything that exists around us. What happened before there were stars, planets, even atoms? Where did the matter that makes up our bodies come from? And what role do violent events like supernovae play in the cycle of cosmic life and death? Is it possible that entire worlds, perhaps with life, orbit other stars, so different and distant that we could never imagine them? Throughout history, human curiosity has driven us to decipher these enigmas. Why does the universe have the shape it does? What secrets lie behind strange phenomena like black holes, quasars, or the mysterious dark matter? How is it possible that events that occurred billions of years ago can leave their mark on the radiation we still detect today? Each answer seems to open new questions, and each discovery brings us a little closer to understanding our place in this vast cosmic stage. On this journey, I invite you to dive into the most astonishing curiosities of the universe, a journey that will take you from the very first moments of the cosmos to the farthest reaches of space and time. Get ready to discover facts that defy logic, paradoxes that still lack explanation, and findings that have forever changed our understanding of reality. Because in the end, the universe is much stranger, more fascinating, and more beautiful than we could have ever imagined. What was there before the universe? This is one of the deepest questions we can ask ourselves, and the answer leads us to the Big Bang, the moment everything began. Approximately 13,800 million years ago, our universe emerged from an extremely dense and hot state. It wasn't an explosion in a place in space, but the sudden expansion of space itself, as if the entire universe were contained in a microscopic seed that suddenly began to grow at an unimaginable speed. During the first fraction of a second, known as the era of cosmic inflation, the universe expanded much faster than the speed of light. How is this possible? The key is that it wasn't matter that was traveling, but space itself that was stretching. In less time than it takes to blink, the universe went from being tiny to encompassing colossal distances. Imagine inflating a balloon from the size of an atom to the size of a galaxy in a fraction of a second. That's how astonishing that first moment was. And what happened next? As the universe continued to expand, it began to cool. In the first few minutes, the simplest elements were formed: hydrogen, helium, and a small amount of lithium. Everything we see today, from stars to planets and ourselves, is made up of these primordial elements. But how do we know all this? Thanks to cosmic background radiation, a thermal echo that we can still detect in all directions, offering us a snapshot of the universe when it was just 375,000 years old. The Big Bang not only marked the beginning of space and time, but also the start of all the physical laws we know. However, there are still unresolved mysteries. What caused the Big Bang? Did a before really exist? Current physics cannot answer with certainty, as the extreme conditions of that moment challenge even our most advanced theories. The fascinating thing is that every time we look at the night sky, we are observing remnants of that primordial event, a trace that continues to expand and transform the universe we inhabit. Dark matter and dark energy are undoubtedly two of the greatest enigmas of the cosmos. How is it possible that most of the universe is made up of something we cannot see or touch? When astronomers observe the movement of galaxies, they notice that these rotate much faster than they should, according to the amount of visible matter they contain. If only the matter we can see existed, galaxies would simply disintegrate, but they don't. This led scientists to propose the existence of an invisible matter that holds everything together: dark matter. Dark matter does not emit, absorb, or reflect light. making it completely invisible to traditional telescopes. However, its presence is inferred by the gravitational effects it exerts on visible matter. It's like trying to guess the shape of a sculpture covered by a sheet. You don't see it directly, but you can feel its influence on everything around it. According to current estimates, approximately 27% of the universe is composed of dark matter. Despite decades of research, no one has managed to directly detect a dark matter particle. Could it be that we are looking in the wrong place, or that its nature is even stranger than we imagine? But the mystery doesn't end there. If dark matter is already puzzling, dark energy challenges our understanding even further. Observations made in the late 20th century revealed that the universe is not only expanding, but doing so at an accelerating rate. What force drives this acceleration? The answer, at least for now, is dark energy, a form of energy that seems to be present throughout space and constitutes about 68% of the total content of the universe. Imagine inflating a balloon and discovering that, instead of needing more force to blow it up, the balloon starts to expand on its own, faster and faster. That is, on a grand scale, what scientists observe in the universe. Without dark energy, gravity should slow down the expansion, but the opposite is happening. Although many theories have been proposed, we still do not know exactly what dark energy is or how it works. The only certainty is that, adding dark matter and dark energy together, we are surrounded by a universe whose majority is completely unknown. Thus, 95% of the cosmos remains shrouded in mystery, reminding us of how much there is still to discover.
If you're enjoying this journey through the universe and want to keep exploring more cosmic mysteries, don't forget to subscribe to the channel and give the video a like. Thank you for being part of this Star Odyssey.
Did you know that there are regions in the universe where gravity is so intense that nothing can escape, not even light? These cosmic enigmas are called black holes, and their existence challenges our understanding of reality. Black holes are not holes in the literal sense, but incredibly dense objects where a large amount of mass is concentrated in a tiny space. It all begins when a massive star, at the end of its life, collapses under its own weight. If the remaining mass is sufficient, gravity overcomes all known forces and a black hole is born. But what exactly happens inside a black hole? Science still doesn't know for sure. What we do know is that there is an invisible boundary called the event horizon. It's like the point of no return. Once something crosses that limit, there is no turning back. Neither particles, nor radiation, nor even information can escape its pull. It's a deep mystery, and one of the great questions of current physics is whether the information that falls into a black hole is lost forever, or can somehow be recovered. Black holes not only devour matter, they can also grow and merge with each other, releasing enormous amounts of energy. When two black holes collide, they generate gravitational waves, vibrations in the fabric of space-time that scientists have managed to detect with specialized instruments. These mergers are so violent that, for a brief moment, they can release more energy than all the stars in the universe combined. Can you imagine the magnitude of that event? It's like two invisible monsters colliding in the darkness, sending waves that traverse the cosmos. Additionally, there are different types of black holes. The smallest, called stellar mass black holes, can have a mass several times that of our Sun. Supermassive black holes, on the other hand, reside at the center of almost all galaxies, including our own, and can contain the mass of millions or even billions of suns. Despite their destructive power, black holes also play a fundamental role in the evolution of galaxies and in the dynamics of the universe. The mystery of what occurs inside them, where the known laws of physics cease to apply, remains one of the greatest challenges of science. What secrets do these monsters of space hold? For now, they are the closest doors we have to the unknown. What object can have the mass of the Sun, but compressed to the size of a city? Such are neutron stars, the incredible remnants left after the death of a massive star in a supernova explosion. When a star, much larger than our Sun, exhausts its fuel, its core collapses under its own weight, crushing protons and electrons into neutrons. The result is a sphere so dense that just a teaspoon of its material would weigh more than a mountain. Can you imagine it? Matter in its most extreme form, where atoms have collapsed to the limit. And what happens to these neutron stars? Some spin at astonishing speeds, up to hundreds of times per second, emitting beams of radiation that sweep through space like cosmic beacons. These objects are called pulsars. If you were near one, you would hear a kind of regular pulse, like the heartbeat of a galactic heart. In fact, when astronomers first detected these signals, they thought they might come from intelligent life. What makes these signals so precise? It's the stable rotation of the star and its intense magnetic field, which channels energy into beams that we can detect from Earth. The gravity on the surface of a neutron star is so intense that any object would fall towards it at unimaginable speeds, crushed in less than an instant. Moreover, the magnetic fields of some pulsars are so strong that they can rip particles from the surrounding space and accelerate electrons to colossal energies, generating radiation detectable over enormous distances. There are pulsars that spin so fast they complete a rotation in less than a millisecond, making them some of the most precise and fastest objects in the known universe. But why are they so important for science? Neutron stars and pulsars act as natural laboratories where the laws of physics are tested under conditions impossible to replicate on Earth. Their study has allowed scientists to understand matter in extreme states, the physics of gravity, and the mysteries of magnetism on unimaginable scales. Even the detection of gravitational waves caused by the collision of two neutron stars has opened a new window to observe the cosmos. Thus, these objects not only fascinate for what they are, but they also help us unravel the deepest secrets of the universe. Did you know that some of the most powerful and spectacular explosions in the universe, supernovas, are essential for life as we know it? When a massive star runs out of fuel, its core collapses under the weight of its own gravity and, in a fraction of a second, releases an amount of energy so great that it can outshine an entire galaxy for weeks. But what really happens during a supernova, and why are these cosmic events crucial for our own origin? During a supernova, the brutal pressure and temperature are so extreme that chemical elements are created that did not exist before. The calcium in your bones, the iron in your blood, the oxygen you breathe, and even the gold in a piece of jewelry were forged in the hearts of stars that exploded billions of years ago. Thus, every heavy atom that makes up our planet and our bodies is, literally, recycled stardust through colossal explosions. Without supernovas, the universe would be composed almost exclusively of hydrogen and helium, lacking the essential ingredients for life and rocky planets. A fascinating question is, how many types of supernovas are there and how do they differ? Mainly, there are two major categories. Type 2 supernovas occur when a massive star, at least 8 times larger than our Sun, reaches the end of its life and collapses. On the other hand, Type Ia supernovas arise in binary systems, when a white dwarf star steals matter from its companion until it reaches a critical limit, triggering a thermonuclear explosion that completely destroys the star. The latter is so consistent in its brightness that astronomers use it as a kind of cosmic ruler to measure distances in the universe. In addition to creating new elements, supernovas release enormous amounts of energy and matter into space, seeding clouds of gas and dust that can later form new stars and planets. In fact, it is thought that the very formation of the solar system was stimulated by the shockwave of a nearby supernova. Without these events, the cycles of stellar birth and death could not be renewed, and the cosmos would be a much more monotonous and empty place. In summary, although supernovas may seem destructive, they are actually the engine of cosmic renewal. They are the invisible architects that, through their violent death, sow the necessary ingredients for life in the universe. The next time you look up at the sky and see a star, remember that its final destiny could be to become a supernova and perhaps, one day, become part of another world or another life. What exactly is a galaxy? Imagine a city, but on a cosmic scale. A galaxy is a gigantic grouping of stars, planets, gas, dust, and dark matter, all held together by gravity. There are billions of galaxies in the observable universe, and each one can host anywhere from millions to trillions of stars. Did you know that there are galaxies as small as a single cloud of stars and others so large that they defy our imagination? The Milky Way, our home, is just one of them and contains approximately between 100 billion and 400 billion stars. Galaxies do not come in just one type. They are primarily classified into three shapes: spiral, elliptical, and irregular. Spirals, like ours, have majestic arms that swirl around a bright core, resembling a whirlpool of light. Ellipticals, on the other hand, look like giant spheres or eggs and lack that harmonious structure. Irregulars, finally, defy symmetry and appear chaotic, as if they are the result of cosmic collisions. Why are there so many different shapes? The answer lies in the history of each galaxy. Collisions, mergers, and the influence of the gravity from their neighbors shaped their appearance over billions of years. Have you ever wondered how big galaxies really are? The Milky Way, for example, has a diameter of about 100,000 light-years. That means if you could travel at the speed of light, it would take you 100,000 years to cross it from one end to the other. But there are even more colossal galaxies. The Andromeda Galaxy, our closest neighbor, is even larger and is approaching us. In about 4 billion years, both galaxies will collide and, after a gravitational dance, merge into one, reshaping the sky and creating a new star city. Galaxies are not solitary entities. They often cluster together in groups and superclusters, forming a structure resembling a cosmic web. It's as if the universe is woven by filaments of galaxies, connecting vast regions through gravity. At the heart of many galaxies, including ours, lies a supermassive black hole, capable of devouring entire stars and shaping the fate of millions of star systems. What mysteries do these cores hold? We still don't know for sure, but studying them helps us understand how the entire cosmos was formed and evolved. Galaxies, ultimately, are the fundamental building blocks of the universe, true cosmic cities where the greatest story ever told unfolds. What are quasars, and why do they fascinate astronomers so much? Quasars are, in fact, extremely luminous cores of distant galaxies. Their name comes from the expression quasi-stellar radio sources, because when they were discovered, they appeared to be stars, but their energy emissions were inexplicable. How can such a small-looking object shine brighter than hundreds of galaxies combined? The answer is astonishing. Quasars derive their energy from supermassive black holes that devour matter at a dizzying rate at the center of their host galaxies. Imagine a cosmic bonfire so intense that even though it is billions of light-years away, its light reaches us and shines brighter than the entire galaxy surrounding it. That is the power of a quasar. When gas and dust spiral into the central black hole, friction and pressure generate temperatures of millions of degrees, releasing jets of energy that shoot across the universe. If the sun could observe a quasar, it would look like a firefly next to a spotlight. In fact, a single quasar can emit up to 1,000 times more energy than the entire Milky Way. But why are quasars so important for understanding the universe? Quasars are like beacons that illuminate our past, as most of those we observe today exist at such enormous distances that their light left them billions of years ago. Studying them is like looking at an old photo album of the universe. They show us what primitive galaxies were like and how black holes evolved in the dawn of the cosmos. Through their light, scientists can analyze the composition of gas and dust between galaxies, uncovering secrets about the matter that exists between the great clusters of stars. Are there still active quasars near us? Most known quasars are found in the farthest corners of the observable universe, indicating that they were much more common in the past. Today, in the nearby universe, quasars are rare. but their study remains essential. They help us understand the life cycle of galaxies and the extreme processes occurring in their cores. Each quasar is a window into the distant past, a reminder that, in ancient times, the universe was much more violent and energetic than we can imagine. Thus, quasars continue to be one of the great mysteries and treasures for those seeking to decipher the history and structure of the cosmos. The Milky Way is much more than a luminous band in the night sky. It is our galactic home, a gigantic spiral that houses between 100 billion and 400 billion stars. But what is it really like? If we could observe our galaxy from the outside, we would see a majesty of spiral arms swirling around a central core. This core, incredibly dense and bright, is inhabited by a supermassive black hole called Sagittarius AI, which contains a mass equivalent to about 4 million suns. What role does this black hole play? It holds the galaxy together, like the hub of a wheel keeps the spokes in place. Have you ever wondered how many years it takes for the Sun to make a complete orbit around the galactic center? The answer is astonishing. Approximately 225 million years. That is the duration of a galactic year. During all that time, entire civilizations have risen and fallen on Earth, while our solar system barely completes a single orbit in the Milky Way. Not only does the Sun move, every star, planet, and cloud of gas dances in a complex ebb and flow, following the gravitational pull of the invisible mass that permeates the galaxy. The Milky Way is not a lonely island in the cosmos. It is part of a collection called the Local Group, composed of over 50 galaxies, including the famous Andromeda, which is slowly heading towards us. In fact, in about 4 billion years, the Milky Way and Andromeda will merge in a cosmic collision of unimaginable proportions. But what will happen then? Although it sounds catastrophic, the vastness between the stars means that most will pass by without colliding, as if two clouds gently intermingle in the sky. Where do we fit into all this? Our solar system is located in one of the spiral arms, called the Orion Arm, about 27,000 light-years from the galactic center. If the Milky Way were a large city, we would live in a quiet suburban area, far from the hustle and bustle of the center, but with a privileged view of the cosmic spectacle that surrounds us. Moreover, the galaxy is in constant change. Stars are born and die, clusters migrate, and interstellar matter is recycled to form new generations of suns and planets. Thus, the Milky Way is much more than our stellar neighborhood. It is a gigantic cosmic ecosystem in perpetual transformation, full of mysteries yet to be discovered. When we think of planets, we often imagine those orbiting our sun. But did you know that there are thousands of worlds orbiting other stars? These planets are called exoplanets, and their discovery has revolutionized our view of the universe. But how can we detect a planet that is so far away, invisible even to the most powerful telescopes? The answer lies in patience and the observation of tiny clues. One of the most successful techniques is the transit method. Astronomers observe how the light from a star slightly diminishes when a planet passes in front of it, as if a tiny fly were gliding in front of a lamp. Another technique is radial velocity, where the slight wobble of a star caused by the gravity of a hidden planet is measured. Until just a few decades ago, we didn't know if planets were common or a cosmic rarity. Today, thanks to space telescopes like Kepler and TESS, we have confirmed the existence of over 5,000 exoplanets. These worlds present an incredible variety. Some are gas giants that orbit very close to their stars, known as hot Jupiters, while others are rocky and Earth-like, some even located in the so-called habitable zone, where conditions could allow for the presence of liquid water. Can you imagine a planet where a year lasts only a few days, or one whose clouds are made of molten iron? Reality surpasses fiction. One of the big questions raised by the study of exoplanets is, could any harbor life? Scientists are looking for atmospheres that contain oxygen, methane, or water vapor, signals that could indicate biological processes. However, the distance is so great that for now, we can only analyze the light that passes through those atmospheres, giving us just a glimpse of their secrets. Each new exoplanet discovered is like a piece of a puzzle that helps us understand the diversity of solar systems and puts our own place in the galaxy into perspective. But how many exoplanets could really exist throughout the Milky Way? Estimates suggest that each star could have at least one planet, which would bring the total number to hundreds of billions. This makes the possibility of finding life, even in simple forms, seem not so far-fetched. As technology advances, astronomers hope to identify not only Earth-like planets, but also direct signals of extraterrestrial life. Thus, exoplanets have become one of the most fascinating and promising fields of modern astronomy, reminding us that the universe is full of surprises, waiting to be discovered. Why, in such a vast universe, have we not found clear signs of intelligent life beyond Earth? This question lies at the heart of the Fermi paradox, an enigma that has puzzled scientists and thinkers for decades. If there are billions of stars in our galaxy and many have planets in habitable zones, where is everyone? The silence of the cosmos is so profound that it seems to defy logic. Are we an exception in the vastness, or do we simply not know where to look? Some scientists suggest that perhaps intelligent life is extremely rare, or that civilizations tend to self-destruct before they can communicate on a large scale. Others propose that the signals we seek may not be the right ones, or that life could take forms so different from ours that we simply do not recognize them. Imagine searching for radio messages when perhaps other civilizations use technologies completely unknown to us, as if you were trying to catch a text conversation using an old radio. The search for life does not stop at listening to space. We also explore exoplanets in search of atmospheres that reveal signs of biological activity. What if life exists, but is so far away that its signals have not yet reached us? The size of the universe is so overwhelming that even an advanced civilization could be isolated by the distances. Moreover, there is the possibility that some civilizations deliberately choose silence, fearing the risks of being discovered, as if all the lights of a city went out as soon as someone looked in its direction. There are even more intriguing theories, such as the Galactic Zoo, which suggests that advanced civilizations observe humanity without intervening, just as humans observe wild animals without altering their behavior. Other ideas point to the possibility that we may never coincide in time, as life can arise and disappear over scales of millions of years. The Fermi paradox invites us to reflect on our place in the universe and to continue seeking answers, aware that, for now, the greatest mystery is the silence of the cosmos itself. What makes one planet a giant and another a dwarf? In our solar system, the difference is much more than just size. Giant planets, like Jupiter and Saturn, are true colossi primarily made up of gases like hydrogen and helium. To put it in perspective, if Earth were a marble, Jupiter would be a beach ball, and it could hold more than 1,000 Earths inside. These giants do not have a solid surface like ours. Instead, they are enormous gas spheres with possibly rocky cores hidden beneath immense layers of clouds and storms. Their atmospheres are so dense and deep that if you tried to descend into them, you would never find solid ground beneath your feet. Now, what about dwarf planets? You've probably heard of Pluto, the most famous of them all. But why did Pluto lose its planet status? The answer lies in the astronomical definition. To be considered a planet, an object must orbit the Sun, have enough mass to be spherical, and have cleared its orbit of other objects. Pluto meets the first two, but its orbit is filled with other icy bodies. Thus, along with Eris, Haumea, Makemake, and Ceres, it is part of the exclusive family of dwarf planets, which are usually small, icy, and often found in the outer reaches of the solar system beyond Neptune. Did you know that giant planets can have fascinating ring systems and dozens of moons? Saturn is famous for its shimmering rings, although Jupiter, Uranus, and Neptune also have their own rings, albeit much less visible. Moreover, These planets act almost like miniature solar systems, with moons so diverse that some, like Titan or Europa, spark scientists' interest in the search for life. In contrast, dwarf planets, though tiny, are not lacking in oddities. Pluto, for example, has an atmosphere that appears and disappears depending on its distance from the Sun and its moon. Charon is so large in comparison that some astronomers consider them to form a binary system. What do these contrasts teach us? While the gas giants dominate the outer solar system with their gravity and majesty, dwarf planets remind us that even the smallest bodies can have surprising stories to tell. From colossal storms on Jupiter that last for centuries to ice mountains on Pluto that defy imagination, each type of planet provides valuable clues about the formation and evolution of the solar system. In the end, both giants and dwarfs are essential pieces in the cosmic puzzle we are trying to decipher. What really differentiates a comet from an asteroid? Although both are known as the wanderers of the solar system, their origin and composition set them apart as two very distinct types of travelers. Comets, for example, can be imagined as dirty snowballs that formed beyond the orbits of the giant planets, in the icy confines of the solar system. When one of these bodies approaches the Sun, the heat causes the ice and volatile compounds to sublimate, creating that characteristic luminous tail that can extend for millions of kilometers. Asteroids, on the other hand, are usually metallic or rocky bodies that primarily orbit between Mars and Jupiter, in what is known as the asteroid belt. Unlike comets, asteroids do not have tails, as they lack the ice and volatiles that can evaporate. Did you know that some scientists believe that comets may have been responsible for bringing water and organic molecules to primitive Earth? Billions of years ago, during the so-called late heavy bombardment, countless comets and asteroids impacted the surface of our planet. This cosmic bombardment not only brought destruction, but also seeded the basic elements for life. If you've ever wondered where the water in the oceans comes from, the theory of comets as water carriers is still debated, but it offers a fascinating explanation of how the ingredients for life may have traveled through space. But how dangerous are these wanderers to our planet? Asteroids can pose a real threat. The famous impact that wiped out the dinosaurs about 66 million years ago was caused by an asteroid about 10 kilometers in diameter. The energy released was equivalent to the explosion of millions of nuclear bombs. However, most asteroids and comets that cross Earth's orbit are much smaller, and the Earth's atmosphere usually disintegrates them before they reach the ground. Still, scientists constantly monitor these objects to anticipate any potential threat. Is there any famous comet? Without a doubt, Halley's Comet is one of the most renowned. Its appearances, every 76 years, have been recorded since ancient times and have inspired myths and legends in different cultures. For their part, asteroids also have their own notable representatives, such as Ceres, the largest in the asteroid belt, which was even considered a dwarf planet. Both comets and asteroids are witnesses to the primitive history of the solar system, authentic space fossils that allow us to understand how our cosmic neighborhood emerged and evolved. Thus, every time one of these travelers streaks across the sky, it reminds us that we continue to inhabit a solar system in constant motion, where history continues to be written, stone by stone and ice by ice. Did you know that some moons in our solar system might be more fascinating than the planets themselves? While we often think of the moon as the only satellite worthy of attention, the reality is that there are dozens of extraordinary moons orbiting giant planets, and each one holds secrets that challenge our imagination. For example, Titan, Saturn's largest moon, is the only other known place in the solar system where it rains, but not water, rather liquid methane. Its lakes and rivers of hydrocarbons create such an exotic landscape that, in a way, it resembles Earth, albeit in a completely alien and frozen version. Europa, one of Jupiter's moons, is another example of cosmic wonder. Beneath its icy surface lies a saltwater ocean larger than all of Earth's oceans combined. Scientists believe that within this vast underground sea, unknown forms of life could exist. What would you do if you knew that out there, beneath kilometers of ice, creatures completely different from anything we've seen might be swimming. This possibility has driven space missions that seek precisely to find signs of biological activity in this hidden world. But the list of extraordinary moons doesn't end there. Io, another moon of Jupiter, is the most volcanically active place in the solar system. Its hundreds of volcanoes spew sulfur and lava to heights that surpass the tallest mountains on Earth. Imagine a landscape where the ground is constantly changing, where the vibrant colors of sulfur and minerals paint the surface in shades of yellow, red, and orange. This activity is so intense that, if you could be there, you would constantly see explosions and rivers of lava flowing. On the opposite end, we find Enceladus, a small moon of Saturn that, despite its size, hides a warm heart. From its polar cracks, geysers of icy water and organic molecules burst forth, forming a ring of particles around the planet. These geysers suggest the presence of an underground ocean, and some scientists believe that this environment could be ideal for life. Thus, each moon tells a different story. Some are frozen worlds with hidden oceans, others are volcanic activity furnaces, and some have dense atmospheres or landscapes shaped by the most extravagant chemistry. Exploring these moons not only helps us understand the solar system, but also invites us to wonder how many other amazing worlds await us beyond. What makes the Sun so special among the hundreds of billions of stars that exist in the galaxy? The Sun is the source of all the energy that enables life on Earth. Its core burns at over 15 million degrees Celsius, where every second it transforms about 600 million tons of hydrogen into helium through the process of nuclear fusion. Did you know that the energy that warms you today began its journey from the solar center thousands of years ago? The light, trapped in the dense interior of the star, bounces countless times before finally reaching the surface and launching in just 8 minutes to our eyes. The Sun is not an ordinary ball of fire. It is a sphere of plasma, where the atoms are so hot that the electrons have separated from the nuclei. Why do we never see the Sun go out or flicker like other stars? Its stability is the result of a delicate balance between gravity, which wants to collapse it, and the pressure of the energy generated in its core, which pushes it outward. This perfect dance has allowed the Sun to shine with astonishing consistency for nearly 5 billion years and will continue to do so for many more. How much does the Sun weigh? It is so massive that it accounts for 99.8% of all the mass in the solar system. If the solar system were a scale, all the planets, moons, asteroids, and comets combined would barely move the needle compared to the weight of the Sun. Despite its gigantic mass, its composition is primarily hydrogen, the lightest and most abundant element in the universe. Its surface, called the photosphere, has a temperature of about 5,500 degrees Celsius, enough to emit the white light we see every day. But what about the mysterious phenomena that occur on the Sun? From time to time, enormous solar eruptions throw billions of tons of material into space, sending solar winds that can affect technology and cause auroras on Earth. The Sun also has dark spots, known as sunspots, which are cooler and temporary regions. These spots follow a cycle of about 11 years, during which solar activity increases and decreases, even affecting the climate of our planet. And if you've ever wondered if the Sun could suddenly disappear, the answer is no. It still has about 5 billion years left before it becomes a red giant and transforms the cosmic neighborhood forever. What mysteries do the dancing lights that appear in the polar skies hide? The auroras, known as the northern lights in the northern hemisphere and the southern lights in the south, have fascinated humanity for centuries. But what are these light shows really? It all begins when charged particles from the Sun, known as solar wind, collide with the Earth's magnetic field. This kind of invisible shield deflects most of the particles, but near the poles, some manage to sneak through and penetrate the atmosphere. There, they interact with oxygen and nitrogen atoms, releasing energy in the form of colorful lights that seem to float and undulate like ethereal curtains. Why do auroras display such varied and vibrant colors? The answer lies in the molecules of the atmosphere. When solar particles collide with oxygen, they usually produce green hues and, in less frequent cases, red ones. If the interaction is with nitrogen, the colors can be blue or violet. It's as if each element has its own brush and color palette, painting the night sky with unique shades. Sometimes, auroras can be so intense that they are visible from much lower latitudes than usual, a phenomenon that has been recorded and feared by various ancient cultures as a portent of great events. Have you ever wondered why these lights are only seen near the poles? The key lies in how the Earth's magnetic field channels solar particles toward the north and south. This field acts like a giant funnel, guiding solar energy to the polar regions, where the atmosphere is thinner and the interaction becomes more visible. It is no coincidence that the most famous places to observe auroras are Norway, Iceland, Canada, or Antarctica. In fact, there are historical records that recount how indigenous Arctic peoples interpreted the auroras as ancestral spirits or signs from the gods, showing how science and culture have gone hand in hand in interpreting these phenomena. In addition to their beauty, auroras are a window into the dynamic workings of our planet and its relationship with the sun. During the most intense solar storms, auroras can become extremely bright and cover vast stretches of the sky, but they can also affect radio communications and electrical systems on Earth. Thus, these flashes not only gift us one of the most impressive natural spectacles, but they also remind us of the powerful connection between our world and the cosmos. Auroras are a living testament to how the energy from the sun travels millions of kilometers to paint the skies of Earth with light. A reminder that even in darkness, the universe finds ways to surprise us. What if time were not the same for everyone? This is one of the most astonishing questions posed by the theory of relativity, completely revolutionizing our understanding of the universe. Albert Einstein demonstrated that time and space are not absolute, but rather intertwined, forming what we now call space-time. According to this theory, the speed at which you move and the intensity of the gravity around you can affect how you experience the passage of time. In other words, time can flow slower or faster depending on where you are and how you are moving. Imagine two twins. One stays on Earth, while the other travels into space in a ship at speeds close to the speed of light. Upon returning, the twin who was traveling will have aged less than his brother who stayed home. This phenomenon, known as the twin paradox, is a direct consequence of special relativity. The key is that at extreme speeds, time dilates. That is, it passes more slowly for those moving faster. This effect, although imperceptible at everyday speeds, has been confirmed with atomic clocks on planes and satellites, showing differences of fractions of a second compared to clocks on Earth. But relativity not only affects time, it also transforms our idea of space. The mass of a very large object, such as a planet or a star, deforms the space-time around it. It's like placing a heavy ball on a stretchy sheet. Everything that comes close to that curve will be attracted to it. That's why gravity is not an invisible force pulling objects, but a consequence of how space and time curve around matter. Have you ever wondered why planets orbit the sun? It's not because the sun pulls them, but because they travel along the curves of space-time that it generates. General relativity also predicts phenomena that today seem like science fiction, but have been observed and measured. For example, the light from a star can bend when passing near a massive object, like a black hole, due to the extreme curvature of space-time. Furthermore, time passes more slowly, the stronger the gravity. Clocks at the top of a mountain run a little faster than those at sea level. Even global positioning systems like GPS constantly correct for these relativistic effects so that we can locate ourselves accurately. Relativity teaches us that we live in a flexible universe where time and space are not what they seem at first glance. It forces us to rethink concepts we took for granted and to accept that reality is much more surprising than we could imagine. How far can the consequences of relativity go? Perhaps we still have much to discover about the true nature of time and space. What would it be like to travel from one star to another? Interstellar space is so vast that it is almost unimaginable. The distance between our Sun and the nearest star, Proxima Centauri, is over 40 trillion kilometers. If we tried to cover that distance with a spacecraft like the current Voyager probes, which travel at nearly 60,000 kilometers per hour, it would take us more than 70,000 years to arrive. Thus, a fundamental question arises. Is there any limit to the speed at which we can travel through the universe? The answer is provided by modern physics. The maximum possible speed in the universe is the speed of light, approximately 300,000 kilometers per second. Nothing known can exceed this limit. Even light, which seems instantaneous to our eyes, takes more than 4 years to travel from Proxima Centauri to Earth. But why can't we go faster? According to Einstein's theory of relativity, the faster an object travels, the harder it becomes to accelerate it. At speeds close to that of light, the energy required to continue accelerating grows enormously, reaching infinity just before hitting that limit. It's like trying to push a door that becomes heavier and heavier until it is impossible to move. Some ideas have emerged to try to overcome this limit, such as the famous warp drives or wormholes, which are very popular in science fiction. Could these technologies allow us to travel to other stars in reasonable times? So far, there is no evidence that they are possible with our current technology or the physical laws we know. For example, a warp drive would require absurd amounts of energy and exotic materials that we still do not know if they actually exist. Wormholes, although mathematically possible, would be unstable and dangerous. They could close before any spacecraft could cross them. So, what real options do we have? Scientists are exploring alternatives like solar sails, which harness the pressure of light to propel spacecraft at much higher speeds than current ones, or probes powered by powerful lasers from Earth. However, even these innovations would take decades or centuries to reach the nearest stars. Interstellar travel, for now, remains a distant dream, limited by the fundamental laws of the cosmos. The speed of light, more than a barrier, is a reminder of the wonder and mystery of the universe, inviting us to continue exploring and challenging the limits of the possible. What if the universe could send messages through space and time? That is, in essence, what gravitational waves are: tiny vibrations in the very fabric of space-time, created by some of the most violent events in the cosmos. But how did we discover that these waves exist? And why are they so important for understanding the universe? It all begins with a prediction by Albert Einstein in 1916, when his theory of general relativity suggested that extremely massive objects, like black holes or neutron stars, could warp space-time and generate ripples around them, similar to the waves formed when a stone is thrown into a pond. For almost a century, these waves remained an extraordinary hypothesis, undetectable by human technology. Why are they so difficult to detect? Because by the time they reach Earth, these waves are incredibly subtle. They alter distances smaller than the size of an atom. However, in 2015, an experiment called LIGO managed to capture for the first time the echo of two black holes merging 300 million light-years away. It was like hearing, for the first time, the oldest and most powerful music of the universe, confirming that space can vibrate and transmit information about events we could never see with light. What is the purpose of capturing these gravitational waves? Beyond demonstrating one of Einstein's most spectacular predictions, they allow astronomers to listen to the universe in a completely new way. Until recently, everything we knew about the cosmos came from light: visible, infrared, ultraviolet. But there are phenomena so extreme that they do not emit light or block it completely. Gravitational waves pass through any obstacle, bringing with them information about black hole collisions, supernova explosions, and even the echoes of the first moments after the Big Bang. They are, in a way, silent witnesses to the deepest secrets of the cosmos. Can these waves reveal even greater mysteries, such as the origin of dark matter or the true nature of time and space? Each new detection is like opening a window to unexplored regions of the universe, allowing us to reconstruct the history of the most extreme and exotic events. Thus, gravitational waves not only confirm that the universe is in constant motion, but they also connect us with its most distant past, expanding the frontiers of human knowledge and demonstrating that, even in the silence of space, the cosmos has much to tell. What if our universe is not the only one? This question has fascinated scientists and philosophers for decades. The idea of the multiverse suggests that there are many other universes, each with its own physical laws, constants, and realities. But where does this theory come from? Modern physics, especially since the development of quantum mechanics and inflationary cosmology, has opened the door to the possibility that our universe is just one among an unimaginable number of parallel universes. One of the most intriguing theories is that of cosmic inflation, which proposes that in the first moments after the origin of the universe, space expanded at an unimaginable speed. During this process, bubbles of spacetime could have formed, each developing as an independent universe. It's as if the cosmos were a huge loaf of bread in the oven, where each bubble represents a different universe with its own ingredients. Does this mean that somewhere there could be a universe where stars never formed, or where gravity is so weak that planets float aimlessly? Another proposal comes from quantum mechanics and the so-called many worlds principle. According to this interpretation, every time a quantum event occurs, the universe splits, giving rise to alternative realities in which every possibility is realized. For example, in one universe, you might be watching this documentary, and in another, perhaps you never became interested in the cosmos. Could this explain phenomena that seem random, or even the apparent perfection of the physical laws that allow for the existence of life? However, the key question remains: can we detect or interact with these other universes? So far, there is no direct evidence for the existence of multiverses. Most of the evidence is indirect and arises from mathematical calculations and theoretical extrapolations. Some scientists hope that in the future, anomalies in the cosmic background radiation or unusual patterns in the structure of the universe might give us clues of collisions or contacts with other universes. Still, the idea of the multiverse remains one of the most mysterious and exciting frontiers of science, reminding us how small and special our own corner of the cosmos can be. What would change in our perception of reality if one day we confirmed that we are not alone, not even as a universe? Has the universe always been the same size? For a long time, astronomers believed that the universe was static, but just a century ago, Edwin Hubble discovered that galaxies are moving away from each other, which means that the universe is expanding. However, what is truly surprising is that this expansion is not constant, but is accelerating. It's as if you threw a ball into the air, and instead of slowing down due to gravity, it started moving faster and faster upward. Why does this happen? The answer leads us to one of the greatest mysteries of cosmology: dark energy. This mysterious component, which accounts for about 7 out of every 10 parts of the universe, acts as a repulsive force that drives the accelerated expansion of the cosmos. Scientists detected it indirectly by observing distant supernovae, which appeared dimmer than expected. This could only be explained if the universe were expanding at an ever-increasing rate. But what is dark energy really? No one knows for sure. Some think it is an inherent property of space, while others suspect it could be the effect of a new form of field or energy still unknown. What are the consequences of this accelerated expansion? If the universe continues to expand faster and faster, distant galaxies will eventually move away so much that the light they emit will never reach us. In a very distant future, the inhabitants of the Milky Way might look up at the sky and see a practically empty universe with no signs of other galaxies. This possible fate is known as the Great Tear, where even atoms could disintegrate if the expansion becomes intense enough. Although this would happen billions of years from now, The idea of a universe constantly moving away from itself is as unsettling as it is fascinating. To measure this acceleration, scientists use concepts like the Hubble constant and increasingly precise observations of the cosmic microwave background, the radiation that reaches us from the earliest moments of the universe. Thanks to these studies, we know that the expansion began to accelerate about 5 billion years ago, roughly the same time that the Sun and Earth were forming. But will we ever fully understand what drives this mysterious force? For now, the accelerated expansion of the universe serves as a reminder that, while we have made great strides in our understanding of the cosmos, fundamental questions still await answers. What is the oldest signal we can detect from the universe? The answer is cosmic microwave background radiation, a kind of fossil echo that has existed for nearly 14 billion years. This radiation is like a photograph of the universe when it was just 380,000 years old, an instant after the Big Bang. At that moment, the universe cooled enough for protons and electrons to combine and form hydrogen atoms, allowing light to travel freely for the first time. That light, stretched and cooled by the expansion of the cosmos, reaches us today as a faint microwave radiation that permeates all of space. But how do we know it's really there? It was in 1965 when two scientists, Arno Penzias and Robert Wilson, accidentally detected a persistent noise signal while working with an antenna. At first, they thought it was an error, perhaps pigeon droppings on the equipment. But soon they discovered they were listening to the cosmic microwave background radiation, the irrefutable proof that the universe had a hot and dense beginning. Since then, this radiation has been studied in detail, and its analysis has allowed scientists to reconstruct the early history of the universe with astonishing accuracy. Why is this radiation so important? Because it contains the imprint of the first density fluctuations, small variations in temperature and energy that, over time, gave rise to galaxies, stars, and planets. It's like looking at the seeds of everything that exists today. If the cosmic microwave background radiation were completely uniform, the universe would be a dull and empty place. But those tiny irregularities allowed matter to clump together and form the structures we observe in the cosmos today. Furthermore, the study of cosmic microwave background radiation has allowed the validation of many cosmological theories. Thanks to missions like COBE, WMAP, and Planck, scientists have been able to accurately measure the composition of the universe, its age, and its geometry. Even small differences in the temperature of the radiation, on the order of 100,000th of a degree, contain valuable information about dark matter and dark energy. In short, cosmic microwave background radiation is a window to the distant past, a kind of backdrop that connects us to the origins of space and time. Without this faint signal, our understanding of the universe would be much more limited. Every time scientists fine-tune their instruments to listen to this primordial echo, they get a little closer to answering some of the deepest questions about the origin and fate of the universe. Have you ever wondered why day suddenly turns to night, or why at times we see the moon seemingly disappear? These wonders of the sky have names: eclipses and planetary transits. An eclipse occurs when a celestial body comes between a light source and another object, casting its shadow. The most well-known is the solar eclipse, where the moon perfectly aligns between the Earth and the Sun, blocking its light for a few minutes. In a lunar eclipse, it is the Earth that interposes itself, leaving the moon bathed in a faint reddish glow. This color, known as blood moon, is due to the Earth's atmosphere filtering sunlight, allowing only the reddish tones to reach the lunar surface. Did you know that, on average, a specific location on the planet can take up to 400 years to experience a total solar eclipse? Planetary transits are another fascinating spectacle, although much less frequent and noticeable to the naked eye. They occur when a planet passes directly between its star and the observer, casting a tiny shadow. The transit of Venus, for example, was key in measuring the distance between the Earth and the Sun in the 18th and 19th centuries. To give you an idea, The next transit of Venus won't happen until the year 2117. Why are they so rare? Because planets and Earth do not orbit in exactly the same plane, so perfect alignment is uncommon. If we think about it, observing a transit is like watching a small dot slowly move across a giant flashlight. It requires patience and precision. Some eclipses and transits have marked the history of science. For instance, the experimental verification of Einstein's theory of relativity took advantage of a solar eclipse to observe the apparent shift of stars near the Sun, demonstrating that gravity can bend light. Transits, on the other hand, are a fundamental tool in the search for exoplanets. When a planet passes in front of its star, the light we receive diminishes slightly, allowing us to detect distant worlds that would otherwise be invisible. Thus, every time we study these phenomena, we are not only witnessing a natural spectacle, but also deciphering the secrets of the cosmos. But what determines the duration and type of eclipse? It all depends on the orbits, sizes, and relative distances between the involved bodies. That's why there are total, partial, and annular eclipses, each with its own rules and beauty. In annular eclipses, the moon is farther from the Earth and does not completely cover the Sun, creating a brilliant ring of fire. Partial eclipses, on the other hand, only darken a portion of the celestial body. Each variant shows us the precision and mathematical dance that governs the universe. Observing an eclipse or a transit is, in reality, contemplating celestial mechanics in action, a cosmic choreography where every movement is perfectly calculated. Why does the universe seem so old, and how do we know how many years it has? Determining the age of the cosmos has been one of the most exciting challenges in science. For centuries, humanity could only speculate about its origin and duration. But today, we have scientific methods that allow us to calculate the age of the universe with surprising precision. The most accepted answer by the scientific community is that our universe is approximately 13,800,000,000 years old. But how did we arrive at such an impressive number? One of the main methods for calculating the age of the universe is to observe the so-called redshift of galaxies. The farther away a galaxy is, the faster it is moving away from us, indicating that the universe is expanding. If we imagine the universe as a balloon being inflated, the galaxies would be like small spots on the surface. As the balloon inflates, they all move away from each other. By calculating the current rate of expansion, scientists can rewind that process and estimate when everything began to expand, the moment of the Big Bang. But that's not all. The cosmic background radiation, that faint glow that permeates all of space and is the echo of the Big Bang, also gives us crucial clues. By analyzing its temperature and the small variations in it, astronomers can deduce how much time has passed since the universe was a hot, dense soup. It's like finding the embers left after a big bonfire and, from their heat, calculating how long it has been since the fire was burning brightly. Are there other methods to verify these results? Yes. The study of globular clusters, which are groupings of very old stars, allows us to calculate the minimum age of the universe. If we find stars that are, for example, 13 billion years old, we know that the universe must be at least as old as they are. All these methods, surprisingly, converge on the same age range. Measuring cosmic time is a challenge because, at such enormous scales, concepts like a year or a century seem tiny. To put it in perspective, if we compress the entire history of the universe into a single year, human civilization would have emerged only in the last seconds of December 31st. Thus, the age of the universe not only reveals its antiquity, but also highlights the brevity of our existence in comparison. Every piece of data, every technique, brings us a little closer to understanding our place in the vastness of the cosmos. The stars have fascinated humanity since time immemorial, but how do we make sense of the apparent chaos of the night sky? Thousands of years ago, different civilizations began to connect imaginary dots between the stars, forming shapes known as constellations. These groupings not only served to tell stories and myths, but were also fundamental tools for navigation and timekeeping. The ancient Egyptians, for example, relied on the appearance of certain constellations to predict the flooding of the Nile, while Greek and Phoenician sailors used the North Star in the Little Dipper constellation to orient themselves on their nighttime journeys. Thus, looking at the sky was, in a way, like reading a gigantic map drawn with light. Did you know that constellations vary by culture and time? While in Europe, they spoke of Orion, the hunter, in other regions, like Australia, the Aboriginal people saw the same stars as the figure of an emu. Today, the International Astronomical Union has established 88 official constellations that cover the entire celestial sphere, as if the sky were divided into perfectly fitting puzzle pieces. However, many of the traditional stories and names survive and are passed down from generation to generation, filling the firmament with mythology and legends. Celestial cartography, or the art of mapping the sky, has been key to scientific advancement. How did astronomers manage to create accurate maps before the invention of the telescope? They used tools like the astrolabe and the sextant, measuring angles between the stars to locate their exact position. This knowledge allowed not only for maritime navigation, but also for the development of agricultural and religious calendars. In a way, studying the sky was a way to organize life on Earth, anticipating important seasons and rituals. Thanks to these maps, today we can locate stars, planets, and phenomena like meteor showers with great precision. Do constellations still have utility today? Beyond their historical and cultural value, constellations are essential for modern astronomy. They serve as a reference system for locating any celestial object, from a distant galaxy to a fleeting comet. Astronomers divide the sky into regions associated with each constellation, making it easier to study and catalogue the countless celestial bodies. Thus, every time we look up and recognize a shape in the stars, we are using a tool that has accompanied humanity for millennia, connecting science, history, and wonder in a single glance at the universe. Have you ever wondered what the universe is really made of? At first glance, we might think that everything is composed of common matter, like that which makes up our bodies, the Earth or the stars. However, the reality is much more fascinating. The elements of the universe are the fundamental building blocks of all matter. From hydrogen, the simplest and most abundant, to the more exotic and rare elements, each has its own cosmic story. Hydrogen and helium, for example, were born in the first minutes after the Big Bang. Later, in the hearts of stars, heavier elements like carbon, oxygen, and iron were forged in a process known as stellar nucleosynthesis. But what about the even heavier elements, like gold, platinum, or uranium? These do not form in ordinary stars. This is where one of the most astonishing stories of the cosmos comes into play: supernovae and neutron star collisions. When a massive star explodes in a supernova, it releases such an amount of energy that it allows for the creation of heavy elements, scattering them across space. In the case of two neutron stars merging, the collision is so violent that even rarer and more valuable elements are generated, like the gold we wear in rings and jewelry. Thus, the universe recycles and distributes its ingredients in an endless dance. Did you know that, despite the immense variety of elements, most of the visible universe is made almost entirely of just three: hydrogen, helium, and oxygen? Hydrogen accounts for approximately 3/4 of ordinary matter, followed by helium, which makes up most of the rest. Oxygen is the third most abundant, and it is essential for life as we know it. Elements like carbon, nitrogen, silicon, and iron are much less abundant, but they are crucial for the formation of planets, atmospheres, and living beings. Heavier elements like lead or uranium are true rarities, present in tiny proportions that, however, can change the fate of entire worlds. Where are the rarest elements of the universe found? Some, like technetium, do not even exist stably on Earth, but have been detected in dying stars. Others, like francium, are found in such small amounts that they could fit on the tip of a pin across our entire planet. There are even artificial elements, created in laboratories by humans and not found naturally in any corner of the cosmos. These elements, mostly radioactive and ephemeral, help us better understand the fundamental laws of matter and energy. Thus, the elements of the universe not only tell the story of matter, but also that of transformation, destruction, and cosmic rebirth. Every atom in our bodies has traveled through space for billions of years, forged in ancient stellar furnaces, or born from titanic explosions. We are literally stardust, a unique mixture of common and rare elements, united by chance and physics, and privileged witnesses to the eternal alchemy of the universe. Did you know that planetary rings are not exclusive to Saturn? Although this planet is famous for its majestic rings, other giants of the solar system like Jupiter, Uranus, and Neptune also have ring systems, although much fainter and harder to observe from Earth. Why does Saturn have the most spectacular rings? The answer lies in the composition and size of the particles that make them up. Saturn's rings are primarily composed of water ice and small amounts of rock, with fragments that can vary in size from a grain of sand to a small mountain. This ice reflects sunlight intensely, making the rings shine with an incomparable beauty in the sky. But where do these rings come from? Scientists believe they are the result of the destruction of moons, comets, or asteroids that came too close to the planet and were torn apart by its powerful gravity, in a phenomenon known as the Roche limit. It's as if the planet traps its reckless visitors and shreds them, scattering their remnants into orbit. In the case of Saturn, it is thought that its rings could be relatively young on a cosmic scale, perhaps formed only a few 100 million years ago, which is just a blink in the life of a planet. The structure of the rings is much more complex than it appears at first glance. Although from afar they seem to be solid bands, they are actually made up of thousands of individual rings, some as thin as a building and others as wide as a continent. There are also gaps within the rings, like the Cassini division, which are not absolute voids, but areas with a lower concentration of particles, caused by the gravitational influence of nearby moons known as shepherd moons. These moons act as guardians, maintaining the order and shape of the rings through their gravity, creating patterns and waves that travel through the ring system like waves in a pond. Will planetary rings last forever? Studies indicate that they are in constant change and will likely disappear over time. The particles that compose them can be attracted by the planet or expelled into space, and the rings tend to become thinner over time. In the future, Saturn could lose its rings and become a planet visually similar to Jupiter. Thus, planetary rings remind us that even the most impressive wonders of the cosmos are ephemeral, and that the universe is in constant transformation, guided by physical laws that, although invisible, weave celestial landscapes of astonishing beauty and mystery. When we think of space, we often imagine an absolute nothingness, an infinite void where absolutely nothing exists. But is it really like that? The spatial vacuum is one of the most fascinating and, at the same time, most misunderstood concepts of the universe. Although at first glance it might seem that between the stars and planets there is nothing but an immense desert of nothingness, the reality is much more complex and surprising. To begin with, the spatial vacuum is not completely empty. Even in the most distant regions of galaxies, there are tiny particles, such as solitary hydrogen atoms, cosmic rays traveling at speeds close to that of light, and a faint haze of interstellar dust. If we could take a spoonful of intergalactic vacuum, we would probably find just a few atoms throughout its volume. However, this sparse content is enough to create extraordinary phenomena. In fact, the vacuum is so low in density that here on Earth, the best laboratories cannot replicate a region as empty as deep space. But what other strange properties does the vacuum have? One of the most surprising is that the vacuum is full of energy. According to quantum physics, even in the total absence of matter, there are always tiny and spontaneous fluctuations of energy, known as vacuum fluctuations. These fluctuations can create and destroy pairs of particles and antiparticles, in very brief times, in a phenomenon known as the quantum sea. It's as if the vacuum were a kind of invisible and effervescent ocean, where nothing is truly static or silent. Can the vacuum have effects on matter? The answer is yes, and in really astonishing ways. One example is the so-called Casimir effect, in which two metal plates very close to each other in a vacuum feel a force pushing them together due to quantum fluctuations. Furthermore, the accelerated expansion of the universe seems to be driven by what is called vacuum energy, also known as dark energy, a mystery that still challenges modern science. Thus, far from being a simple backdrop, the spatial vacuum is a silent and dynamic protagonist, shaping the fate of the cosmos in ways we are just beginning to understand. Did you know that thousands of meteorites fall to Earth every year, but most are so small that they disintegrate before hitting the ground? Meteorites are fragments of rock or metal that travel through space and, after surviving the intense heat of the atmosphere, reach the surface of our planet. But where do these cosmic visitors really come from? Most originate in the asteroid belt between Mars and Jupiter, where constant collisions launch debris into space, turning them into true messengers of the beginnings of the solar system. Can a meteorite tell the story of the universe? The answer is fascinating. Yes. Each meteorite is like a time capsule. Some contain minerals that do not exist on Earth, while others enclose tiny grains of dust older than the Sun itself. Thanks to the study of these fragments, scientists have discovered that many meteorites are over 4.5 billion years old, allowing us to learn about the composition and conditions of the primitive solar system. Amino acids, the fundamental building blocks of life, have even been found in meteorites that have fallen to our planet. Could it be possible that the ingredients for life came from space? Not all meteorites are the same. There are metallic ones, primarily composed of iron and nickel, rocky ones, which resemble Earth stones but have a much older origin, and mixed ones, which combine both materials. Some meteorites, like the famous Hoba meteorite in Namibia, weigh tens of tons, while others are tiny and go unnoticed. What are the chances of one impacting near you? Although the possibility is very low, Earth constantly receives dust and small fragments without us realizing it. It's as if we are under a silent rain of particles from outer space. The impact of meteorites has had dramatic consequences in Earth's history. Did you know that it is believed that the extinction of the dinosaurs was caused by a large meteorite that struck the Yucatan Peninsula 66 million years ago? This event released energy equivalent to millions of atomic bombs and forever changed the course of life on the planet. But meteorites have not only brought destruction, they have also delivered water and essential compounds for life. Thus, every meteorite we find is not just a rock fallen from the sky, but a witness to the origins and evolution of both Earth and the universe. What exactly is gravity, and why is it so fundamental in the universe? Gravity is the invisible force that keeps the Earth orbiting around the Sun, that prevents us from flying off our planet, and that allows the existence of galaxies, stars, and planets. But even though we feel it every day when we walk or when an object falls to the ground, this force remains one of the great mysteries of physics. Did you know that, of the 4 fundamental forces of the universe, gravity is the weakest, yet also the most dominant on large scales? While magnetism or nuclear forces only act over tiny distances, gravity has an infinite reach, guiding the fate of everything that exists. Why do all objects fall at the same speed, regardless of their weight? Galileo Galilei demonstrated this in the 17th century by dropping 2 spheres of different masses from the Leaning Tower of Pisa. Both objects reached the ground at the same time, defying the intuition of the time. This happens because gravity pulls on all bodies with the same acceleration, as long as there is no air resistance. Later, Isaac Newton described gravity as an attractive force between masses. The greater the mass of an object, the stronger its gravitational pull. Thus, the Sun, with its enormous mass, keeps the planets orbiting around it, as if they were marbles trapped in a curved track. But is gravity simply a force? Or is there something deeper? Albert Einstein revolutionized our understanding by proposing that gravity is, in fact, a curvature of space-time caused by mass. Imagine an elastic sheet. If you place a heavy ball in the center, the fabric deforms, and any smaller object that passes nearby will roll toward it. Thus, planets are not tied to the sun, but rather follow curved paths created by the deformation of space-time. This idea explains astonishing phenomena such as the movement of Mercury or the existence of black holes, places where gravity is so intense that even light cannot escape. Gravity also plays a crucial role in the birth and death of stars. It is the force that gathers gas and cosmic dust to form new stars, and the one that ultimately collapses the core of a dying star, giving rise to exotic objects like white dwarfs, neutron stars, and black holes. It even influences time. In the presence of very intense gravity, such as near a black hole, time passes more slowly. This strange consequence, confirmed by experiments and satellites, demonstrates that gravity not only shapes space, but also the very flow of time. And there are still unanswered questions. Why is gravity so weak compared to other forces? Is there a fundamental particle, the graviton, responsible for transmitting gravity? Could there be hidden dimensions where this force disperses? As scientists seek these answers, gravity remains the silent architect of the universe, weaving the structure of the cosmos and maintaining the delicate balance necessary for the existence of life. Without it, the universe would be a chaos of particles floating randomly, without form or purpose. At the heart of black holes lies one of the greatest enigmas of the universe, the event horizon. This invisible boundary marks the point of no return, the threshold beyond which nothing, not even light, can escape. But what really happens at that mysterious edge? Does matter disappear forever, or does its information somehow survive? Here lies the paradox of the event horizon, a dilemma that perplexes even the brightest physicists. The paradox arises when we combine two fundamental pillars of physics: general relativity and quantum mechanics. According to relativity, everything that crosses the event horizon is irretrievably trapped, doomed to an unknown fate inside the black hole. However, quantum mechanics tells us that information cannot be destroyed, not even under the most extreme conditions of the cosmos. How is it possible for both principles to be true at the same time? Is information lost in the black hole, or does it somehow manage to escape? One of the most intriguing ideas is the so-called holographic information. Some scientists propose that all the information of objects falling into a black hole is encoded on the event horizon itself, as if it acts as a kind of superficial memory of the universe. Imagine a sheet of paper where everything that happens in 3 dimensions is recorded in just 2. Thus, the horizon would be the surface where the past of everything that enters is etched, even though we never see it come out. But if that's the case, how could we retrieve that information? Is there any mechanism that allows information to escape in the form of radiation? This is where the famous Hawking radiation comes into play. This radiation, theoretically predicted, allows black holes to lose mass and eventually disappear. But the great dilemma is that Hawking radiation seems to be completely random, containing no trace of the original information. This phenomenon has sparked one of the most intense debates in modern physics. If black holes disappear, does the information evaporate as well, thus challenging quantum laws? Or perhaps, does the information release itself in a way we are yet unable to comprehend? The paradox of the event horizon remains without a definitive solution, and it has become a theoretical laboratory to explore the limits of human knowledge. Solving this mystery could revolutionize our understanding of space, time, and the very nature of reality. Will it ever be possible to fully understand what happens at that invisible threshold? Or will the event horizon continue to guard the deepest secrets of the universe? Time and science will be the judges of this fascinating paradox. Have you ever thought about how a star is born? It all begins in vast clouds of gas and dust called nebulae. There, under the invisible embrace of gravity, matter starts to concentrate until it forms an increasingly dense and hot sphere. When the temperature in the core reaches millions of degrees, nuclear fusion is unleashed. Hydrogen atoms begin to fuse to form helium, releasing an enormous amount of energy. Thus, a new star ignites its light, as if it were a spark in the cosmic darkness. But how long can a star shine? Surprisingly, its life depends on its mass. Small stars like our Sun can live for tens of billions of years, while the larger ones consume their fuel in just a few million years. It's like comparing a candle that burns slowly with a firework that is consumed in an instant. For most of its existence, the star remains stable, balancing the weight of its own gravity with the pressure of the energy it generates in its core. And what happens when the fuel runs out? The fate of a star depends again on its mass. Medium-sized stars, like the Sun, expand and transform into red giants, sometimes engulfing nearby planets. Then, they shed their outer layers and leave behind a dense, hot core called a white dwarf, which glows faintly for billions of years before cooling completely. However, the most massive stars meet a much more dramatic end. They explode in a supernova, an event so bright that for a brief period it can outshine an entire galaxy. After the explosion, what remains? If the star was massive enough, its core can collapse to form a neutron star, an object so dense that a teaspoon of its material would weigh millions of tons on Earth. And if the mass is even greater, gravity becomes unstoppable and leads to a black hole, a region of space where not even light can escape. Thus, the life of a star is a fascinating cycle of birth, splendor, and transformation, leaving behind the elements that will form new stars, planets, and perhaps life itself. What would happen if there were a mysterious kind of reflection in the universe capable of nullifying reality as we know it? This is the fascinating story of matter and antimatter, two opposite sides of the same cosmic coin. Matter is everything that makes up our world, from stars, planets, and living beings to the air we breathe. But for every particle of matter, physics predicts the existence of an identical companion in mass, but with an opposite charge, the antiparticle. Thus, for example, the electron, with a negative charge, has its evil twin, the positron, which has the same mass but a positive charge. And what happens when a particle and an antiparticle meet? The result is as spectacular as it is definitive. Both annihilate each other in a flash of pure energy. This reaction, known as annihilation, releases photons, particles of light, and is one of the most efficient processes of mass-to-energy conversion that exists. In fact, if we could harness this interaction in everyday life, a small amount of matter and antimatter could generate an unimaginable amount of energy, far greater than any conventional explosive. However, antimatter is extremely scarce in the observable universe. Why don't we see galaxies made of antimatter? What prevented both from completely annihilating each other after the birth of the cosmos? The answer to this mystery is one of the great open questions of modern physics. The most accepted model suggests that, during the first moments after the Big Bang, there was almost the same amount of matter as antimatter, but for reasons still unknown, there was a slight excess of matter. For every billion particles of antimatter, there was 1,000,000,001 of matter. That slight imbalance was enough that, after the great annihilation, all that remained was that small residue of matter, which ended up forming stars, galaxies, and life. What mechanism caused this asymmetry? Scientists are currently exploring phenomena such as CP symmetry violation, but the definitive explanation remains an enigma. Is it possible to create or find antimatter today? Yes, but with great difficulty. In laboratories like CERN, physicists manage to produce small amounts of antiparticles, which are immediately captured before they come into contact with matter and are destroyed. Antimatter already has practical applications. In medicine, for example, it is used in positron emission tomography, an advanced imaging technique for detecting diseases. However, storing antimatter is one of the greatest technological challenges, as any contact with ordinary matter causes its instant annihilation. Thinking about matter and antimatter is peering into a universe where duality and balance play a fundamental role. They are proof that reality can have opposite reflections, and that, even in the apparent simplicity of the everyday, there are deep and astonishing secrets. Could we one day use antimatter as a source of energy, or even as fuel for space travel? For now, it remains one of the most intriguing and mysterious frontiers of physics, a reminder that, in the universe, every answer often opens the door to new questions. Singularity is one of the most perplexing and fascinating concepts in modern physics. What happens when matter is compressed to a point where known laws cease to function? At the heart of a black hole, all mass collapses into a single point of infinite density and zero volume, the singularity. Here, space and time, as we understand them, lose all meaning. It's like trying to divide by zero in mathematics. The result simply has no explanation within our known rules. Classical physics and Einstein's general theory of relativity predict the existence of these singularities, but paradoxically, they cannot describe what happens inside them. Why? Because at that extreme limit, gravity becomes so intense that space-time curves infinitely. It's as if you were trying to describe the inside of a tornado using only the calm air of a sunny day. It just doesn't fit. Here, quantum mechanics also comes into play, but it too lacks clear answers, as there is still no unified theory that combines gravity with the quantum world. Could the singularity be a doorway to another dimension, or even another universe? It is one of the most provocative questions in cosmology. Some scientists speculate that, instead of a point, the singularity could be a region where the laws governing our universe break down or transform completely. However, so far, no one has been able to directly observe a singularity, as it is shielded by the event horizon, that invisible boundary that even light cannot cross back. The singularity poses one of the greatest challenges for physics. What really happens in that place where time and space collapse? Solving this enigma could open the doors to a new era of knowledge, where the impossible becomes possible and our understanding of the universe is radically transformed. Until then, the singularity remains the ultimate enigma, the boundary where current science stops and the realm of the unknown begins. What if I told you that gravity not only attracts planets and stars, but can also bend light, as if space were a kind of cosmic lens? This phenomenon, known as gravitational lensing, is one of the most astonishing demonstrations of Albert Einstein's general theory of relativity. But what does it really consist of? When an extremely large mass, such as a galaxy or a cluster of galaxies, stands between a distant light source and us, the gravity of that object curves the space around it, deflecting the rays of light that pass nearby. It's as if the universe placed an invisible magnifying glass between our eyes and the distant cosmos. Did you know that thanks to this effect, astronomers can see objects that would otherwise be completely hidden from our view? Gravitational lensing can create distorted images, magnify distant galaxies, and even multiply the image of a single object into several parts of the sky. Sometimes, this phenomenon generates luminous arcs, or nearly perfect rings, known as Einstein rings, formed when the alignment between the light source, the massive object, and Earth is nearly exact. These arcs and rings are like the fingerprints of the universe, revealing the presence of matter that we cannot see directly. But why does this happen? According to relativity, mass deforms the fabric of space-time, just like a heavy ball sinks into a stretchy sheet. When light travels near a large concentration of mass, it follows the curvature of that space, altering its path. This deflection is so precise that astronomers use the gravitational lensing effect as a tool to measure the mass of entire galaxies, including those parts made of dark matter, which does not emit light and would be invisible without this trick of nature. Moreover, the gravitational lensing effect not only allows us to study the visible universe, but also to discover planets outside the solar system, observe galaxies formed billions of years ago, and map the distribution of dark matter. How is it possible that a simple curvature of light reveals so many secrets? The universe, through gravity, offers us a window to the invisible, bending light so we can look further and understand how the cosmos is constructed. The gravitational lensing effect is undoubtedly one of the master keys to deciphering the mysteries of deep space. The universe is immense and seemingly silent, but is it really in absolute silence? If we could travel through space, we would realize that the vacuum does not allow sound transmission as it does on Earth. On our planet, sound travels through the air, but in interstellar space, there isn't enough matter for those waves to propagate in the same way. However, this does not mean that the universe is completely mute. How is it possible then that scientists talk about the sound of the universe? The key is to remember that sound waves are, in essence, vibrations. In space, even though we cannot hear with our ears, there are vibrations in plasma, gas, and interstellar dust. For example, at the center of some galaxy clusters, astronomers have detected pressure waves that resemble sound waves, but with frequencies so low that we would need millions of years to hear even a note. A fascinating case is that of the Perseus cluster, where pressure waves have been recorded that, if translated into musical notes, would sound much deeper than anything we can perceive. Can you imagine a cosmic symphony so slow that a single vibration lasts for years? Does this mean that astronomers can hear the universe? Not in the traditional sense, but they can translate these vibrations and waves into audible sounds for humans. Using data captured by telescopes and probes, scientists convert fluctuations in energy, radiation, and magnetic fields into sound frequencies. Thus, phenomena like the echoes of gravitational waves produced by the collision of black holes or the regular pulses of pulsars are transformed into sounds that we can hear here on Earth. This technique, called sonification, allows us to explore the cosmos through hearing, opening a new dimension for science and art. But there's more. Even the cosmic microwave background, the residual whisper of the Big Bang, can be heard if translated into audio signals. This primordial echo, which permeates the universe, contains the imprint of the first moments after the birth of the cosmos. When scientists convert this data into sound, what we get is a soft murmur, a kind of white noise that encapsulates the oldest history we can know. In short, although the universe does not sound like an orchestra in open space, it does have a voice that reveals itself only to those who know how to translate the invisible mysteries into melodies that, although inaudible to our senses, connect us with the origin and structure of the cosmos. Have you ever wondered if there is a limit to what we can see in the universe? When astronomers talk about the observable universe, they refer to the portion of the cosmos that we can detect, study, and measure from Earth. But why is there a limit? The reason is the speed of light. Although the universe is immense, light takes time to travel. We can only observe objects whose light has had enough time to reach us since the beginning of the universe. It's like being in a large, dark room, illuminated only by distant flashlights. You only perceive the lights that are on and what is around them, but what lies beyond remains in darkness. The observable universe has an approximate radius of 46 billion light-years. However, this number does not mean that this is the age of the universe, but rather that space itself has been expanding while the light traveled. In fact, many of the galaxies we see at the edges of the observable universe no longer exist as we see them. We are witnessing a kind of old photograph, a frozen image of a distant past. The expansion of space causes the limits of what is observable to shift constantly, but there are regions that, no matter how long we wait, will never become visible. Here arises an intriguing question. What lies beyond that edge? The universe does not have a wall, nor does it end abruptly. Beyond the observable universe extends the so-called unobservable universe, a region that we will never be able to see or receive information from, as the light from those places is, and will always be, beyond our reach due to the accelerated expansion of the cosmos. It's as if we lived on an island surrounded by an infinite sea, and no matter how much we sail, we could never reach the horizon because it moves away at the same speed or faster than our boat. This boundary, called the cosmological horizon, not only limits what we can observe but also what we can know. There are theories suggesting that the universe could be infinitely large, or even that there could be regions with different physical laws than ours. However, everything we know, everything we can measure and understand, is confined to our observable universe. The rest remains an absolute mystery, reminding us how small our window to the cosmos is and how many secrets await us in that invisible vastness. The universe is full of enigmas that challenge our logic and test the limits of our knowledge. Why, if the laws of physics seem so solid and universal, are there questions that even the brightest scientists cannot answer? One of the most famous paradoxes is Schrödinger's cat, a thought experiment that shows how, in the quantum world, an object can be in two opposing states at once. Can something be alive and dead at the same time? Quantum mechanics suggests that yes, at least until we observe it. This leads us to wonder if reality depends on our observation. Another fascinating mystery is the information paradox in black holes. Classical theory states that nothing can escape from a black hole, not even light. However, according to quantum physics, information is never destroyed. So, what happens to the information of objects that fall into a black hole? Stephen Hawking proposed that it could disappear, but this conflicts with the fundamental laws of physics. Scientists have yet to find a definitive answer, and the solution to this enigma could change our understanding of the cosmos. The Olbers paradox also challenges our intuition. If the universe is infinite and filled with stars, why is the night sky dark? Logic suggests that in any direction we look, there should be a star illuminating the sky. The answer involves the expansion of the universe and the fact that the light from the most distant stars has not yet reached us, as well as many having burned out over time. However, this mystery continues to fuel debates and theories about the very nature of the cosmos. Finally, there is the Fermi paradox, a question that arises when looking at the vast dimensions of the universe. If intelligent life should be common, where is everyone? Billions of stars, countless planets, and yet no clear trace of advanced civilizations. Is it possible that we are the only ones, or do we simply not know how to search? Some hypotheses suggest that civilizations self-destruct before they can communicate, while others propose that they simply do not want to be found. This cosmic silence is one of the great mysteries that invites us to keep exploring and questioning our place in the universe. Thus, the unresolved paradoxes and mysteries remind us that, no matter how much we advance in knowledge, there will always be questions that challenge our understanding. It is these enigmas that drive human curiosity and keep the fascination with the universe alive, inspiring us to seek answers beyond the imaginable. What awaits the universe in the future? This question has fascinated scientists and philosophers for generations. Although we do not possess a cosmic crystal ball, astronomers have gathered a series of theories based on observations and precise calculations. Everything points to the universe being in constant expansion. But will it continue this way forever? Or will there come a time when its fate changes? One of the most discussed theories is the so-called Big Freeze. According to this hypothesis, the expansion of the universe will never stop. Galaxies will drift further apart, stars will exhaust their fuel, and gradually, darkness will prevail. In this scenario, the temperature of the universe will drop to near absolute zero, and all available energy will dissipate. Imagine it like a campfire that, after burning for a long time, leaves only cold ashes and darkness. But is the Big Freeze the only possible end? Some scientists propose the Big Crunch, a sort of reverse of the Big Bang. If gravity manages to overcome expansion, the universe could start contracting, collapsing upon itself until it reaches an extremely dense and hot state. However, current observations suggest that the expansion is accelerating, making this scenario increasingly unlikely. Another intriguing hypothesis is the Big Rip. In this case, dark energy, that mysterious force driving the accelerated expansion of the universe, would become increasingly dominant. There would come a time when the expansion would be so violent that it would tear apart galaxies, stars, planets, and even atoms. It would be as if the fabric of space-time were ripping into pieces. Beyond these possible endings, there are even more speculative ideas. Could a new universe arise after the death of ours? Are there infinite cycles of expansion and contraction? Current models do not entirely rule out these possibilities, although we still lack conclusive evidence. Despite significant advances in cosmology, the ultimate fate of the universe remains one of the deepest mysteries. Whatever the future holds, the truth is that the universe, like everything in nature, is in constant change and evolution. How much do we really know about the universe? Despite centuries of observation and study, we continue to uncover secrets that challenge our imagination. The universe is so vast and complex that every answer seems to open the door to new questions. Why is there something instead of nothing? What lies beyond what we can see? These questions, as old as humanity itself, remain unanswered, keeping alive the flame of curiosity that drives us to explore. As we look up at the sky, we encounter phenomena that seem to defy the laws of nature. Black holes that devour light, stars that explode and scatter the elements of life, entire galaxies dancing in a cosmic choreography dictated by gravity. How can matter organize itself into such diverse forms, from invisible particles to structures spanning millions of light years? The universe is like an immense book, of which we have barely read the first pages. Science has managed to unravel some of the deepest mysteries, such as the composition of stars, the birth of planets, or the existence of invisible forces like dark matter. However, for every mystery solved, another even more puzzling one arises. Is the universe infinite, or does it have an edge? Could there be other universes, so different from ours that their own physical laws would be incomprehensible to us? The possibility of life beyond Earth, the nature of time, or the ultimate fate of the cosmos are enigmas that, for now, remain beyond our reach. Despite our smallness in the face of the vastness of the cosmos, each new discovery reminds us that we are part of a story much larger than we can comprehend. We are stardust, conscious and capable of marveling at the beauty and mystery that surrounds us. The universe is not only the stage of our existence, but also the greatest of teachers, inviting us to look up and never stop asking. What wonders await us in the next turn of the galactic spiral? The exploration continues, and as long as there are questions, there will also be dreams.